Swayam Prabha. Digital India. Educated India.
Hi friends, now we will have a tutorial class, and in this class we will solve some numerical problems based on the topics discussed in the last 4 classes. Our first problem statement is the proximate analysis of a coal sample and its heating value are as follows. So, moisture 2.9%, volatile matter 29.4%, fixed carbon 58%, ash 9.7% and gross calorific value 7650 kilocalorie per kg. So, calculate proximate analysis and calorific value on moisture free basis and dry ash free basis. So, this is the problem statement. So, you have to calculate proximate analysis and calorific value. So, under 2 conditions, one is moisture free and dry ash free basis. It is given moisture, volatile, fixed carbon, ash. So, all the proximate analysis values are provided on as received basis. So, you have to convert it to moisture free basis and dry ash free basis, and accordingly the calorific value also you have to convert. So, let us see, we have different compositions, moisture, volatile matter, fixed carbon, ash and calorific value as received basis. It is given in the statement. Now, if I want to convert these values in moisture free basis, that means we are excluding the moisture. So, this moisture will not be available in this case. So, how much we are having? Total mass will be this one. Out of 100 we will be having 100 minus 2.9. So, 97.1. So, the moisture free basis, the volatile matter will be 29.4 into 100 divided by 100 minus 2.9, that is 97.1. So, that is equal to 30.28. And similarly, fixed carbon will be 58 into 100 divided by 100 minus 2.9, that is equal to 97.1, that is equal to 59.73 we are getting here. Similarly, ash content will be this into this divided by this, that is equal to 9.93. And what will be the calorific value? Calorific value this equal to 32023 into how much? 100 divided by 97.1. So, that is equal to 32979 kilojoule per kg. This is for moisture free basis. Now, for dry ash free basis, we will not be having moisture, we will not be having ash. So, we are getting this plus this. So, in this case volatile matter will be 29.4 into 100 divided by 100 minus, this is 100 minus 2.9 minus 9.7. So, that is equal to 100 minus 12.6, that we are getting. So, that value is converting to 33.64. For fixed carbon we are having 58 into 100 divided by 100 minus 12.6, so 66.36. Then what will be the calorific value? Obviously 32023 into 100 divided by 100 minus 12.6, that we are getting 36,640 kilojoule per kg. So, the problem is solved. Now, our second problem, it says during a boiler trial the coal analysis on mass basis was reported as carbon 62.4%, hydrogen 4.2%, oxygen 4.5%, nitrogen 0.4%, sulfur 0.2%, moisture 14.4%, as 13.9%, and assume average molecular weight of S is equal to 56. Then determine the molecular formula of the coal and the heating value on a as received basis and dry basis using the following. So, these are the relationship it is given for HHB, that is equal to 0.3516 into C, that is the percentage of carbon, plus 1.16225 into H is percentage of hydrogen, and 0.1109 into O, percentage of oxygen, and 0.0628 into N, percentage of nitrogen, plus 0.10465 into S, percentage of sulfur, and LHB in megajoule per kg is equal to HHB minus 0.0244 into W minus 9 is W is the percentage of moisture and H is percentage of hydrogen, it is given. So, we have to determine the molecular formula of the coal and the heating value on as received basis as well as dry basis. Then what we will do? Obviously, we will write the different parameters on as received basis. So, as received basis percentage of carbon we are having as per the statement 62.4, then hydrogen 4.2, oxygen 4.5, nitrogen 0.4, sulfur 0.2, as 13.9 and moisture 14.4, that is in percentage. So, if we assume that 100 gram of material, so carbon is 62.4 gram, hydrogen is 44.2 gram, oxygen 4.5 gram, nitrogen 0.4 gram, sulfur 0.2 gram, as 13.9 gram and moisture 14.4 gram. Now, what are the molecular weight of the element? Carbon has 12, hydrogen has 1, oxygen 16, nitrogen 14, sulfur 32, as 56 and H2O 18. So, how many moles are present in this amount of material? Then we can get 62.4 divided by 12, that is equal to 5.2 for carbon. Similarly, 4.2 divided by 1 for hydrogen, that is 4.2, and for oxygen we are getting 4.5 divided by 16, that is 0.28. For nitrogen we are getting 0.4 divided by 14, 0.028, and for sulfur we are getting 0.2 divided by 32, that is 0.0062, and for S we are getting 13.9 divided by 56, so 0.248, and for moisture we are getting 14.4 divided by 18, that is equal to 0.8. So, these are the moles present in this total 100 gram of the sample. So, we can write this, the molecular formula C 5.2, H 4.2, oxygen 0.28, nitrogen 0.028, sulfur 0.0062, and as 0.248 and H2O 0.8. The one part we are getting the molecular formula, then we have to calculate the heating value both in as received basis as well as in dry basis. So, we have to convert these values, percentage values, from as received basis to dry basis. So, how can you do it? So, dry basis means we will not be having any moisture. So, here we are getting 62.4 into 100 divided by 100 minus this moisture, that is 14.4. So, it is coming to 72.89. Similarly, we are getting hydrogen, that is 4.2 into 100 divided by 100 minus 14.4. So, 4.91. Similarly, oxygen will be 5.26, that is equal to 4.5 into 100 divided by 100 minus 14.4, and here also we will get 0.4 divided by 14.4, and here also sulfur 0.2 into 100 divided by 100 minus 14.4, and here we will be getting 13.9 100 by 100 minus 14.4. So, these are the dry basis compositions we are getting for different elements. Then what we will do, heating value we have to calculate. So, heating value formula is given. So, HHB equal to this formula is given. Now, we have got the value of CHONS. So, we will put those values. C is equal to 62.4 on as received basis, hydrogen is 4.2, oxygen is 4.5, nitrogen is 0.4, sulfur is 0.2. So, by this formula we are getting the HHB is equal to 28.26 megajoule per kg, and LHB this formula is also given. So, HHB equal to this one 28.26. So, minus 0.0244 into W is the moisture content. So, 14.4 and 9 into H equal to 4.2. So, that we are getting 26.98 megajoule per kg, on which basis, as received basis. But if I use this formula on dry basis, this value will change, percentage of C, percentage of H, percentage of O, percentage of nitrogen and percentage of sulfur. So, accordingly our HHB value will also change. As shown here, this is the formula. So, carbon content is changed to 72.89. So, we will put it here. Hydrogen is changed to 4.91, we will put it here, and oxygen is changed to 5.21. So, we will put it here, and nitrogen is 0.47. So, we have put here, and then sulfur is 0.23, and the value is coming 30.81 megajoule per kg. And lower heating value is equal to, again we have formula, but what is the moisture in this case? Is it dry basis? So, we will not have any moisture. So, the W equal to 0 and H equal to 4.9 as it is converted, that is 4.91 we can write. Then LHV is equal to this and as this one. So, it is coming, so 29.7 megajoule per kg. So, now we are able to solve the problem. We have determined the molecular formula, we have determined the heating value, low heating value and high heating value on the basis of adhesive basis and dry basis. Now, we are coming to problem number 3. The statement is, to determine the water equivalent of a Bohm calorimeter 1.1651 gram benzoic acid sample, high heating value 6318 calorie per gram was used. The experiment produced a net corrected temperature rise of 3.077 degree centigrade. The acid titration required 11.9 ml of standard alkali and 8 centimeter of per 45 C10 nickel chromium fuse wire was consumed in firing. So, determine the water equivalent of the Bohm calorimeter. So, this is our problem statement. So, we have to determine the water equivalent of the Bohm calorimeter. So, we have some formula that is equal to water equivalent is equal to high heating value into M, mass of sample taken, then E1 plus E2 plus E3 divided by del T. We have to identify the values of each term in this expression. So, what is the H in this case? H is given in the statement, that is 6318 calorie per gram. What is this M? It is given 1.1651 gram, we have taken it. Then what is E1? E1 can be calculated on the basis of C1. So, what is C1? Alkali amount of alkali solution required in ml for titration, acid titration. So, it is 11.9 ml. So, E1 is equal to 11.9 ml into 1 calorie per ml. So, the 11.9 calorie. Then what will be the E2? E2 will come from C2. We have C2, there is no sulfur as per the statement. You see here in the statement there is no sulfur. So, it is benzoic acid used, there is no sulfur. So, that is why C2 is equal to 0, and then E2 is equal to 13.7 into C2 into mass of this. So, that is equal to 0, and E3 is coming from C3. So, 2.3 into C3 as it is say 45 C, as it is we are using 45 C10 nickel chromium fuse wire. So, for this expression is applicable. So, 2.3 into 8 centimeter it is used. So, 8 into this 18.4 calorie. So, now we have got all those values and del T value is also given. So, what will be the W? This into this one plus this one plus this one divided by del T. So, we are getting 2402.1 calorie per degree centigrade. So, this is the water equivalent of the calorimeter. Now, our problem statement is for a coal fired utility boiler, the temperature of high pressure steam would be about 540 degrees centigrade and T cold, the cooling water temperature, the cooling tower water temperature would be about 20 degree Celsius. Then calculate the Carnot efficiency of the power plant. And they are very simple. If we see what we have to do, we have to convert this centigrade to Kelvin and then 540 degree centigrade convert it to Kelvin and 813 and then T cold 20 degree centigrade it is equal to 293 Kelvin. Then what is the Carnot cycle? We have some formula, that is efficiency equal to 1 minus T cold by T hot into 100. So, what is T cold? 293. What is TH hot? That is 813. So, we will put this value and we will getting the 64% efficiency. In this connection, one problem we may discuss here also, that a thermal power plant is producing electricity throughout the year. So, in winter and in summer, in which case the thermal efficiency will be higher. So, if we use this equal to 1 minus T cold TH hot. So, as the thermal power plant is the same technology you are using. So, say boiler, say supercritical technology or subcritical, whatever may be. So, TH is fixed. So, efficiency summer TS T cold, that is related to cold, that is ambient temperature we are using for this, if it is. So, T summer and if it is called winter, we are getting winter. So, TS is greater than TW. So, when TS we will put here, obviously the efficiency will be lesser and we will put TW here, we will get more efficiency than that when we put TS in place of T cold. So, that is why in winter the efficiency will be higher. Now, the problem statement number 5. So, here we have to solve this problem. It is given that a conventional coal fired power plant cost $1200 per kilowatt to construct and have an efficiency of 34%. Advanced plants use the clean burning integrated coal gasification combined cycle, that is called IGCC, integrated gasification combined cycle, in which the coal is subjected to heat and pressure to gasify it while removing sulfur and particulate matter from it. Currently, the construction of IGCC plant cost about $1400 per kilowatt, but their efficiency is about 45%. The average heating value of coal is about 2 crores 80 lakhs kilojoule per ton, that is 2 crores 80 lakh kilojoule of heat is released when 1 ton of coal is burnt. If the IGCC plant is to recover its cost difference from fuel saving in 5 years, determine what the cost of coal should be in dollar per ton. The time value of the money may be ignored. So, what we have to calculate? We have to calculate what will be the price of the coal, so that the excess amount of money which is being invested in case of IGCC plant, that can be recovered within 5 years period. So, this is the problem, but normally what happens, 5 years means there will be some changes in the value of the currency money also. So, that part we need not to consider, time of value time value of money may be ignored. So, that is told. So, now let us see, as it is given that we need not to consider the time value. So, directly we will be consider the time, 5 years time it is provided. So, what is the construction cost difference, the conventional power plant and IGCC, that we will see. So, in 1400 minus 1200, so that is $200, $200 costlier the IGCC than the conventional one for 1 kilowatt capacity. So, to 5 years, within 5 years, how much electricity will be generated with the capacity of 1 kilowatt, that we can calculate. Then that much of energy is required in terms of electric energy. So, for that certain amount of heat energy is required, that is related to efficiency of the power plant, and then we will calculate that. Then that amount of energy is coming from the coal basically. So, and heating value of coal is known. So, how much coal is required for both the cases with having different efficiency, that we will calculate, and then on that way we have to see that the $200 is recovered by the use of IGCC by saving of the power or the production of the more electricity. So, that is what we are going to do. So, what is our first objective? We have to determine how much amount of electricity can be generated with 1 kilowatt capacity for 5 years. So, for 5 years, that will also depend in many factors, maybe the plant is operating with high load or say throughout the year, or it may have some breakdown, anything may be, but we will be assuming that full load is there and 100% utilization is possible. So, in 5 years we will be getting 365 days into 4 plus 1 leap year. So, 366 days. So, this 4 into 365 plus 366 days into 24 hours, that is total is your 43,824 hours we are getting. So, 1 kilowatt is running for 43,824 hours. So, total kilowatt hour we are getting 43,824. So, this is the energy which is produced if the plant is used in full capacity. Now, this is the electrical energy which is produced, but we have two different plants. So, one plant is having less efficiency, other is having higher efficiency. So, we will be finding out the coal requirement to produce this amount of electricity in two different routes, two different plants. And what will be the coal requirement? How much heat divided by heating value of the coal. How much heat, what type of heat? How much heat present in the coal. So, what amount of energy we are using here kilowatt hour, that is electric energy. So, that equivalent of heat energy you have to get it. So, mass of coal that is equal to heat energy divided by heating value of the coal, but this QW has to be correlated with the electrical energy, that is related to the efficiency of the power plant. So, W by efficiency will be in place of QH. Now, M coal equal to this expression we are getting, W by efficiency into HV coal. Efficiency for the conventional method is 0.34 and HV is equal to given 2 crore 80 lakhs kilojoule per ton, and then W is also given, this much of electricity we produced, we need, the plant can produce with full load. So, to produce this amount of electricity we need this amount of coal, that is 16.57 tons of coal is required. These are the conversion. Why this 3600 second? Because we are having kilowatt and joule, it is given in kilojoule. So, watt has to be converted into joule. So, that is a joule per second. So, that hour has been converted to second. So, that is 3600 second has been put here. So, this is our 16.57 tons we are getting. But for the second case, for IGCC plant, what will be the coal requirement? That is also same formula, QH by HV coal and then W by efficiency into HV coal. So, this case efficiency is 0.45. So, other parameters are same. So, here because of this higher value of this, our coal requirement is less, that is 12.52 tons. So, for 16.57 minus 12.52 is equal to the coal saved we are getting by the use of this IGCC plant. So, this coal save means we are using less amount of money, that should be equivalent to how much investment we have made for the installation of the IGCC plant. So, that is equal to 4.05 tons of coal can be saved over the 5 years for 1 kilowatt of plant capacity, for 1 kilowatt of plant capacity. So, what will be the cost of it? So, that will be 200 we have to save from this, that is the 4.05 tons. So, $200 by 4.05 tons, that is equal to $49.37 per ton. So, that was the question which was asked. So, we have solved it now. Now, it can be possible that plant is not running with full load. So, with the how much efficiently it is running, that will vary, that will also influence this one. So, one another case just I have shown you, that is if it is a if the plant only produced 75% of the maximum possible kilowatt hours over a given 5 years, then the saving will be 4.05 into 0.75, that is equal to 3.04 ton. In this case, the $200 has to be recovered from this. So, 200 divided by 3.04. So, price of the coal will be, so the price will be $65.83. Okay. So, now we have solved all the problems. So, thank you very much for your patience.